Hey everybody, so this is going to be our last little thing. This is our last week for this year. I will probably, I don't know whether I'm going to continue doing these at some point or whether I'm going to stop doing them entirely. I haven't yet decided. I've quite enjoyed doing them. But doesn't matter. What matters is whether they're useful or not. We're going to talk about algebraic proof. Okay, and algebraic proof is one of those key cornerstones of maths when you get outside of GCSE level, okay? And it's the ideas of how you look to prove things start to resonate throughout A-level maths, throughout degree level maths, throughout post-degree level maths, and just the kind of that is an entire essence of maths starts off with us looking at algebraic proof. Okay, and the first thing to kind of understand about algebraic proof is what algebraic proof actually does, okay? And the very first slide we're going to do is going to hopefully show us why we need algebraic proof, okay? So let's do that, okay? And let's just change. There we go. That gives us a little bit more space now, doesn't it? So let's say, as an example, that we were wanting to work with two consecutive odd numbers, okay? And consecutive is a word that we're going to see a lot of, and it essentially just means that the numbers that are next to one another, okay? So 1 and 2 are two consecutive integers, so we could take two consecutive odd numbers, for example, 3 and 5. They're consecutive odd numbers. If we square them and add them together, what do we notice? Okay, well, 3 squared is 9. 5 squared is 25. 9 add 25 gives us a nice 34. What do we notice? Well, not a whole lot. I mean, the only thing that we can tell is that this thing is even. Okay? And if we choose another pair of consecutive odd numbers, does it work again? All right, then. Let's try 7 and 9. So 7 squared is 49. 9 squared is 81. 49 add 81 gives us 130, which is even. Okay. Now what we've done here, we've not proved that if we take two consecutive odd numbers, square them and add them together, we get an even number. What we've done is we've shown that if we take two consecutive odd numbers, square them and add them together, we get an even number. Okay. The difference between showing and proving is that showing relies on you doing it kind of once. Okay, you can show it for an example, or you can show starting at something just to show that something happens. The difference between a show and a proof is that a proof does not deal with numbers like we've done here. What a proof will do, it will have to remove the number that you're working with, so you're dealing with an abstract concept, okay? And in this case, the abstract concept is algebra, okay? This is why we call it algebraic proof. So what we're going to do is we're going to look to build up a scaffold so that we can prove statements like this, okay? And the place that we start is by knowing how to represent certain ideas with algebra. Okay, so these are some examples of concepts that we might use, okay? And we will need to know some of these as a default, but we may also need to figure out how to arrive at some of them if we can't remember them, okay? So in algebra, if I asked you to think of a number, any number, you would probably tell me a letter. So the way that we can represent any number using algebra is by using any letter. Excuse me. And if I asked you to then think about any other number, any other different number, you would have to think of some other letter. Now, consecutive integers are integers that are next to one another. Okay, so if our first consecutive integer was n, how would we know what the next integer along would be? Well, we'd have to take n, and we would have to add 1 to it. Okay? Now, I could have said that if my first consecutive integer was n take away 1, the next one along would be n. Okay? There's an alternative way of thinking about this, but keeping things nice and positive generally makes things easier. Okay? We'll come back to odd numbers in a second. If we're thinking about an even number, what do we know that always will fit into an even number? Let's think. Our even numbers, 8, 4, 16, 200. What number will always fit into an even number? Now, if you said 2, you'd be absolutely correct. So an even number can always be written as 2 times something else. Okay, and that something else we represent using the letter n. So if even numbers, which are effectively our 2 times table, can be written as 2n, our multiples of 3, which are our 3 times table, we can write as 3n. Okay, don't worry about that red splot. That red splot doesn't need to be there. Okay. Now, this thing with the odd numbers. I find that the easiest way to explain how an odd number gets its representation is to think about the sequence of odd numbers. Okay. Now, we've seen that with even numbers, we represent them by saying 2 times a number. And the reason why is if we look at the nth term for this sequence of numbers, we get that they go up in 2 each time. We don't need to add on or take anything off, so we get the representation 2n. For odd numbers, we still have that they go up in 2 each time, so we still know that it's going to be 2n, but that's the 2 times table. Okay? What the 2 times table does and what the sequence of odd numbers does is something quite different. Okay, so to get from our sequence of 2 times table down to the sequence of odd numbers, we'd have to take away 1. So for our even numbers, we have a sequence of 2n. Our odd numbers, we have a sequence of 2n take 1. However, because dealing with negatives is slightly awkward, it may be easier for us to do 2n plus 1. Okay, and it does still work. The only thing that makes it different is that your numbers have effectively shifted 1 along. Okay, trust me, it's fine, it works, and the fact that we keep things with nice and positive, it makes things that little bit easier than doing with 2n take away 1. Okay, so these are some of our basic representations. We also need to think about some things which might be a little bit more complicated. So consecutive odd numbers. If our first odd number was 2n plus 1, what would I have to add on to that to be able to get to my next odd number? Well, if I added on 1, I would get to an even number, because in between every odd number is an even number. So if I added 2, I would get to my next odd number. So I'd have 2n plus 1 plus another 2, which we can write as 2n plus 3, which is exactly what we have there. And if you did start with 2n take 1, you could have 2n take 1 and 2n plus 1. Absolutely fine. A different even number? Well, we can write an even number as 2n, so if we wanted a different even number, we could just use a different letter. So we could have 2k, or 2p, or 2q, or 2r, or 2a, or anything else, so long as we use a different letter. Now, the wording of this last one is slightly tricky, but the next multiple of 3 to 3n. Now, that means we're looking for the next number that's in our 3 times table after 3n. And the way that we're going to find that is by doing 3n, add another 3, or doing 3 lots of n plus 1. Now, some of these, I would say, are things that we absolutely have to know. We need to know how to represent any number. We need to know about consecutive integers, odd numbers, even numbers, multiples, and consecutive odd or even numbers, okay? Those are ones which, if we know those off the top of our heads and we can recall them nice and quickly, they will help us a lot with being able to do proof-style questions later on. Okay, and I would highly recommend you pausing the video at this point and making note of those representations in your book or on paper or somewhere to hand. Okay, because if you're going to be a master at proof, you're going to need to know these things. Okay, so I would pause the video, get some stuff down before we move on to our next slide. Okay, so here we go. So this slide here is going to be the first of a couple of exercises that I'd like you to do if you have not done proof before. Okay, what we have here are a number of different ways of talking about different things in proof. For example, an even number, or the sum of 2 consecutive odd numbers, or the square of an odd number. Okay, and on the right hand side we've got a list of different expressions that we can get which match up to one of these. Okay, and some of them, like the top 2, we should be able to do just from thinking about what we had in our previous table. Okay, but these other things, we're going to need to know what these different keywords mean. Now, hopefully you do. Hopefully you do know what they mean. Hopefully you remember that sum is talking about adding 2 things together, that a product is talking about multiplying 2 things, and that a difference is talking about doing a subtraction. Okay? One thing that I will say, though, is that when you're doing a square of an odd number, and if we remember, an odd number can be written as 2n plus 1. If you're doing the square of an odd number, that means that you want to square all of 2n plus 1. And remember as well that squaring a bracket like that is the same as writing that bracket next to one another like I've done here. Okay? So, what I would like you to do is to take some time, maybe 10-15 minutes, to see if you can match up the expressions that we have here with the expressions, with the sentences that we have here with the expressions that we have on the right-hand side. Okay? So I want you to pause the video, give yourself about 10-15 minutes, see how much of these you can do, because being able to expand something in this fashion or be able to work with an expression in this fashion can be very, very useful. Okay, so your chance to pause the video is now. Okay, so hopefully you've had a chance to pause the video and have a go at this for yourself. I'm going to start connecting these up. So an even number, that can be represented as just 2n. Okay, an odd number, that can be represented as 2n plus 1. Those are just things which we've said from our previous slide. Okay. The sum of an odd, so 2n plus 1, and an even, 2n. Sum means to add together, so 2n plus 1 plus 2n is 4n plus 1. The sum of two consecutive even numbers, so that might be 2n and 2n plus 2. So if I have that, I'm going to have 4n plus 2, which is just at the top there. And next, we've got the sum of two consecutive odd numbers, so 2n plus 1 and 2n plus 3. Now if I do that, I've got 4n plus 4. Okay, here we go. So you can see how once we think about what this sentence means, we can start to think about what it will mean in terms of algebra. What have we got next? We have the product of an odd, so 2n plus 1, and an even. Now, a product means to multiply, and we can think of that by sticking things in brackets and expanding them like we would expand a bracket. So 2n times 2n, 4n squared, 1 times 2n, 2n. So I'm looking for 4n squared plus 2n, which is just over there. Next, product of two consecutive even numbers. So we've got 2n and 2n plus 2. Again, it's a product, so we're sticking things in brackets and doing some expanding. We've got 4n squared plus 4n. Now I saw that, there we go, over there. Perfect. What do we got next? The product of two consecutive odd numbers. Right, okay. So this is the first occasion where we're going to have to do some proper expanding to make sure that we get this right. Now I've got a double bracket expansion. Whether you use a grid method to do this, whether you use your connections to do this, but you're multiplying everything in one bracket by everything in the other bracket. We're going to have 4n squared plus 2n plus 6n plus 3. Now the 2n and the 6n will simplify together to give us 4n squared plus 8n plus 3. Okay, and that really does rely on our expanding skill. Okay. The difference of two consecutive numbers. Okay, so that should be a bit of a quicker one for us to think about. If we've got two consecutive numbers, two consecutive integers, the difference between them is just 1. Okay, we always have to just add 1 to get from one integer to the next. I can't have many left now. Square of an odd number. Okay. Hang on, have I missed one out? I have missed one out. How about that? Difference of two consecutive numbers. Okay. Hang on a moment. That was the one I just did. What am I talking about? Right. There we go. Difference of two consecutive numbers is 1. There we go. Sum of two consecutive numbers. Okay. Now we're back on track. Sum of two consecutive odd numbers. We're going to have n and n plus 1. So when I add those two things together, I've done it again. N and n plus 1. When I add those two things together, I get 2n plus 1. The square of an odd number, we want to expand this, but we're running out of options very quickly. We're going to have 4n squared plus 2n plus 2n plus 1, which when we simplify, get 4n squared plus 4n plus 1. And that means we've got 1 left. The square of an even number, 4n squared. Okay. Now, I'm not saying that you should be able to read these things on the left-hand side and just know straight away what they are from the right-hand side. What I would expect you to do is to be able to start with the thing that's on the left-hand side, recognize parts of it. So recognize maybe the definition of an odd number, the definition of an even number, and construct the expression from that. Okay? So that is the first step in us being able to do a proof. Okay? Is being able to take a written statement and do something with it. Okay? Now, you might think that we would jump from this step here, what we've got here, to thinking about, to thinking about something like the problem that we had at the beginning of this video. Something like this. And you could do that. You could start with 2 consecutive odd numbers, which we could write as 2n plus 1 and 2n plus 3. We could square them, so I could have 2n plus 1 squared, 2n plus 3 squared, add them together, and then do some algebraic manipulation. Okay? Where I expand the brackets and then simplify what we've been given. Okay? You can jump straight into doing that, okay? But I want us to get a kind of an intermediate stage along the way, which is to think about the processes that go along with this kind of thing, okay? And that intermediate stage comes in the form of a question that might look a little bit like this, okay? Prove that n plus 4 all squared, take 3n plus 4, is equal to n plus 1, n plus 4, plus 8. Okay? Now, I want you to just imagine, okay, that you've already done a stage of working before this. That imagine you've already done you've created your expression. Okay. And this is it. Okay, so it's almost like we've already done this, and we've arrived at this step. Okay, and we might be wanting to prove that it looks like this. We need to use various algebraic skills to get from this step so it looks something like this. And generally how we do that is by first doing some expanding, second doing some simplifying, and then third by doing some factorizing. Okay, that seems to be, I would say, the structure for about 90% of the proofs. Okay, you might find that with the other 10%, one of those stages isn't necessary. Okay, so let's start with that stage one by doing some expanding, and it's normal to start with the left-hand side. Okay, so the left-hand side, if we expand that n plus 4 all squared, we get n squared plus 8n plus 16. Okay, so now I have a line which says n squared plus 8n plus 16 take away 3n plus 4, like that. So now I move on to my second stage, which is to do some simplifying. Now, n squared, there are no other n squared, so that just stays as it is. But I've got 8n here, and I'm taking away 3n. 8n take away 3n is 5n, positive 5n. And I've got 16 here, and I'm taking away 4. Okay, don't worry about the fact that it says take away positive 4. It just says 16, take away positive 4. So it's just 16 take away 4, which is 12. Now, for the question that we've got here, we want it to be some kind of factorized double bracket plus 8. So it would be useful for me to get it so it was n squared plus 5n plus something plus 8. Now, 12 would be 4 plus 8. And it's this thing which I'm going to want to factorize. Okay, we'll do that final step in purple. Now, because we've got something, we've got two things that will multiply together to make n squared, so that's just n and n. I want two numbers that multiply together to make 4. Well, that's either 1 and 4 or 2 and 2. And they have to add up to make 5. Okay, there's 1 times something and 1 times something, add them together, makes 5. That's just 4 and 1. And we can see there's our brackets, and there's our plus 8 right at the end. Okay. So you can see that we had some expanding that was involved, some simplifying that was involved, and then some factorizing which was involved. And that is exactly the same structure, I've done it again, that is the exact same structure that would occur if we were to do this kind of a problem, okay? Grab an expression, do some expanding, I would have to do some simplifying, and then to show that it's even, I would then have to do some factorizing, okay? Now, I've got a series of other questions that are similar to that get you used to this idea of us expanding something, simplifying, doing some factorizing as well. Okay, and it's a good habit to get into that kind of idea of how proofs are structured and how they're laid out, because it will help you later on. Okay, now for the second part of this video, I just want you to do this exercise. Okay, and you should know if you get the stuff on the right hand side of the equal sign, because it should work out just in the way that this one worked out here. Okay. So I would say take another maybe 10 or 15 minutes. We spaced this out over a much longer period of time when we were in school. So I would like you to have a go at trying out these questions here so you can see how you do with getting that structure of expanding, doing some simplifying, and then refactorizing at the end. Remember, you may not have to refactorize something. It could just be that you get your answer after doing some simplifying. And I'm looking at you, 6 and 7. Okay, I'm thinking that that's probably going to happen with 6 and 7. Okay, that's a half-hour video, plus more when you've done the exercises as well, and I would highly recommend that you do the exercises, okay? Proof is something that you don't learn by watching. Proof is something that you learn by doing, okay? As with all maths. So I'm going to leave it there. Email me if you are not sure about anything that I've said in this video, okay? Email me, because then I will be able to help you. And I would say that you have to do that because the Hegarty proof questions for the quizzes, they are not anywhere near as challenging enough as they could be in your exam. Okay, the kind of stuff that I'm covering in these videos will be, but the Hegarty videos and the Hegarty quizzes that I saw did not cover it. Okay, so I'm going to leave it there. Try out this exercise. Email me if you have any problems. That'll do. I'll see you in another one. Ta-ra.